So I said that Bezout's theorem is somehow the special thing about the integers that makes prime factorizations unique. So let's actually do that. Let's prove the fundamental theorem of arithmetic using Bezout's theorem. So we're gonna do a little bit of pieces. So we're starting with this lemma. And this is where Bezout's theorem will enter into it. So the lemma is, if P is prime and P divides A times B, so if P divides the product, then P divides one of the factors. So P divides A or P divides B. And this again is a thing that is not always true. So in the practice problems, as like, an optional extra, but definitely if you're curious, I've included an example where this is not true. So this is always true for the integers, but you can find examples of things very much like the integers where this is not true. So this is still special. Okay, so let's prove it. How do we prove this? So suppose P does not divide A. We'll show P divides B. And just for fun, let's have a little callback to our propositional logic. What are we saying here? We're using the fact that not A implies B, which is essentially what I'm saying here, is equivalent to A or B, which is what I'm saying here. And just if you want to check if this is true, let's look at these two things real fast. I mean, this is false only in one case, and that's when A and B are both false. And we know that an implication is also false only in one case, and that's when it looks like true implies false. And in this case, you can see that's when A and B are both false. So it checks out. So that's how the proof is going to go. Suppose P does not divide A, then P must divide B. And that proves that P, in general, will divide A or B. So, since P does not divide A, we have greatest common divisor of P and A is equal to 1. Because it has to be a divisor of P, and there are only two of those, 1 and P, and we're saying it's not P because it's not a divisor of A as well. So the greatest common divisor of P and A is equal to 1, and by Bezout's theorem, we can write 1 is equal to S times A plus T times P. So we can write this greatest common divisor as a linear combination of A and P. Now, multiply both sides by B, and what we get is B equals SAB plus TPB. And what are we doing? What can we say now? Then P divides AB by assumption. That's this thing up here. And evidently divides P. I don't know what the best way to say this is. But the point is that P divides this thing because it divides this little guy and it divides this little guy. So again, I've said this a million times, so hopefully it's becoming familiar. By our divisibility rules, P has to divide this whole thing. And of course, this whole thing is equal to B. And that is what we wanted to show. We said we were going to show that P divides B, and that is what we just showed. Cool. So this is essentially why you get the uniqueness of prime factorizations, because if P divides a product, then there's no place for it to hide. It has to show up in one of the factors. So let's use this to prove the fundamental theorem. Let me not write out that huge long name again, but let me write a statement of the theorem so that we remember it. So every n greater than 1 has a prime factorization and I'm going to write it a little bit differently just for convenience. So I'm not going to put exponents. I'm just going to say that these don't have to be distinct. So yeah, not necessarily distinct. And furthermore, this factorization is unique up to ordering of the factors. So this is an existence and uniqueness proof. So we're going to do it in those two parts. Existence is nothing special. By which I mean, this is not something that I'm claiming is special about the integers. You can always just essentially factor things until you're not able to factor them anymore. Since that's all prime is, it's just where you stop being able to factor it. So the idea is that if n is not prime, write n equals a times b. So that's essentially what it means to not be prime, is that you can write it as a product. And then you just repeat this process. If a or b is not prime, write it as a product. And then this process will end after finally many steps, and you'll have a unique factorization. Or sorry, you'll have a prime factorization. You don't know it's unique. And again, let me just say quickly, why do we know that this will always end with a prime factorization? That's essentially just what it means to be prime. When you stop being able to write it as a product, that means the number is prime. So you'll always end up with a prime factorization this way. The uniqueness is where we have to say something, or where we're going to bring in Bezout's theorem and our lemma. So suppose we have two factorizations. N equals P1, Pn, k, let's not use n twice, and n equals q1 to ql. And let's suppose that they're different. So let's do a contradiction. So what does this mean? Well, then, after dividing out any common factors, which I mean primes appearing in both factorizations, if they're different, we have to eventually find a prime that does not appear in both. So let's give it a name. Let's say, without loss of generality, P1 is not among the Qi. But then, P1 divides the product of them because it is a divisor of n. I mean, these are both prime factorizations. It's clear that P1 divides n. And so it must divide this thing as well. Except possibly we've divided out some common factors, but that won't affect whether P1 divides it. So P1 divides this product, but P1 does not divide Qi for all I, because we're assuming that they're distinct prime numbers, so neither of them will divide the other. And this contradicts our lemma. Which says that if a prime divides a product, then it must divide one of the factors. And that is what we wanted to show. So we suppose that they are different, and we found a contradiction. So we conclude that prime factorizations are unique.